Welcome to the Explainer Clinic. Today, we're going to diagnose and cure the most common math bugs that trip us up when working with proportional relationships. If you've ever found yourself totally stuck on a scale drawing or wondered why a scaled-up recipe turned out completely inedible, well, you're in the right place. We're tackling these grade 7 pre-algebra concepts head-on today. Here's our agenda for today's clinic. First up, the waiting room, then diagnosing common errors. After that will be visualizing ratios, analyzing a worked counterexample, going over the corrected ratio solution, and wrapping it all up with a ratio mastery self-check. Part 1, the waiting room, catching the math bug. So, ratios. They're literally the foundational building blocks of proportional relationships, right? But man, they are highly susceptible to some easy-to-catch mutations. For instance, have you ever tried to double a recipe by just adding 2 more cups of every single ingredient? Yeah, it usually ends up being a complete culinary disaster. Suddenly your soup is a salt lick, or your cake is basically a brick of flour. And this happens because we intuitively lean on the completely wrong mathematical operation when we try to scale things up in our heads. Moving on to part 2. Diagnosing common errors, the symptoms. Listen, if your math just isn't working out, you're almost certainly suffering from one of these 4 foundational misunderstandings. Let's run through our diagnostic chart. Symptom 1, mixing up parts and wholes. Symptom 2, ignoring measurement units. Like comparing inches to feet without actually converting them first. Symptom 3 is using additive thinking instead of multiplicative thinking. And symptom 4, failing to keep values in the correct sequence, which, believe me, will completely scramble your unit rate. Part 3, visualizing ratios, the X-ray. Okay, let's put a ratio under the X-ray to really see its structural integrity. A lot of errors happen simply because we rush straight to the numbers without visualizing the relationship first. This brilliantly illustrates the difference. We've got 2 blue parts compared to 3 yellow parts. Now that's a very specific part-to-part relationship. But look at the whole circle. It is vastly different to say 2 blue parts than it is to say 2 blue parts out of 5 total parts. It's such a common trap, confusing the pieces with the whole pie. And doing that, it completely alters the constant of proportionality. Think about it. If a question asks for the ratio of blue to yellow, well, it's 2 to 3. But if it asks for the probability of randomly picking a blue piece, it's 2 out of 5. Mixing these 2 concepts up is literally the #1 reason students stumble when trying to identify proportional relationships in tables and graphs. Let's hit part 4, analyzing a worked counterexample, case study. Knowing how to spot these errors in the wild is absolutely crucial. So, let's look at a mathematical patience chart where things went horribly, horribly wrong. We're looking at the mixing unit symptom here. If we're setting up a scale drawing and we compare 3 inches directly to 1 foot without converting them into like units, our scale factor is completely corrupted. It looks like a 3-to-1 ratio. But the cure is simple. You just convert that 1 foot into 12 inches. Boom. The correct relationship is 3 to 12, which simplifies beautifully down to 1 to 4. Now check out the progression happening here. This right here is the classic additive thinking trap. To scale up the ratio 2 to 3, the student mistakenly just added 2 to both sides, arriving at 4 to 5. But remember that ruined recipe from earlier? Ratios absolutely do not maintain their proportionality through addition. Adding completely changes the fundamental relationship between those numbers. Part 5, the corrected ratio solution, the cure. All right, let's reset this problem and rebuild this ratio using the correct mathematical blueprints. The secret? Using multiplicative logic. Instead of adding, we're going to multiply both the input and the output by a scale factor of 2. 2 times 2 is 4, and 3 times 2 is 6. So 4 to 6 maintains the exact same proportional relationship as 2 to 3. And hey, if you mapped this on a coordinate plane, it would form a perfectly straight line passing right through the origin. And finally, part 6, ratio mastery self-check, follow-up appointment. You've seen the symptoms and you've seen the cure, so now it's time for a quick checkup. We need to test your immunity to these common ratio errors. Here is a classic problem right out of the grade 7 standards. If a person walks a half mile in a quarter hour, what's their unit rate in miles per hour? Think really carefully about how you set up this complex fraction. Don't reverse the order. We want miles per hour, so miles absolutely must be the numerator and hours must be the denominator. And remember, dividing rational fractions involves multiplying by the reciprocal. Take a quick second to visualize that. All right, here is the breakdown.
By keeping the order exactly as stated, miles over hours, and preserving that all-important multiplicative reasoning, we set up 1/2 divided by 1/4. By multiplying 1/2 by the reciprocal of 1/4, which is 4/1, we get a clean, proportional unit rate of exactly 2 miles per hour. No units were mixed up, absolutely no addition was used, and the order was perfectly preserved. As we wrap up this explainer, I want to leave you with this thought. These aren't just abstract rules sitting on a whiteboard somewhere. They're the actual, logical blueprints for understanding growth, scale, and rates in the real world. So next time things just aren't adding up in math, or in a recipe, or just in life, stop and ask yourself, should you have been multiplying all along? Thanks so much for joining me on this explainer, and keep looking for the math hiding in plain sight.